Yeah, hi everyone. Thanks for having me. It's a pleasure. I want to talk about our technology that we call industrial computer vision. So a very specific form of computer vision. You'll see a lot of things that might be special to us compared to other CV and AI use cases. I think I don't need to introduce the company. Volkswagen is the largest car manufacturer in Europe. We have over 100 factories worldwide. So whenever we scale something, it scales quite nicely because there's a lot of locations to scale. And we're gonna dive into computer vision. We started back with the technology in 2020, so quite some time ago. So I can give you a quick intermediate picture on how we progressed and where we are at the moment and how to continue. One short flashback to 2020, that was the time when we started off with the technology, had a look into our factories, like what actual use cases are there, what are the ideas that they have, what are the POCs that are ongoing. Of course, there's always a lot of POCs ongoing in all your factories because they're quite independent and they all want to do things on themselves, and it's quite easy to build POCs. So there was a huge lot of projects that we already met and a lot of ideas that people asked us to implement directly, better tomorrow than the day after. So there was quite a huge interest back in 2020 already. But the key challenge was that back at the time, there was really, I would say, none of these applications in real productive use. So as I mentioned, a lot of POCs, but nothing really tangible working full-time 24/7 as we in our car factory needed. So that called out for some kind of overall strategy that we tried to implement with Volkswagen. We started off with some interviews with all these kind of different product owners and projects and so on, and tried to identify the roadblocks that we had. You'll recognize most of them, I guess, because they're not very unique to these kind of ICV, but rather CV in general, but also AI in general. So the key outcome, or the first big surprise for me, was actually that the AI model development, so the hardcore data science, was usually not the key challenge in these products. So once you have the data and once you know what to solve with it, this actually works out quite nicely already back then at the time. What was rather the challenge was here on the right-hand side, so how to integrate this into our huge legacy IT, a standard topic that probably everyone's struggling with. We had a lot of black box suppliers where some smaller startups sell solutions to our factories, and we don't actually know what's inside. We're not owner of the data, we're not owner of the models, so not really the way forward for us if we want to scale. A big thing is the operations concept, right? So building a working solution is only one part of the whole project, but really making it work and then guaranteeing to your internal customers that it works in the end is a big, really big challenge. And of course, there's a lot of IT admin processes in large corporations like Volkswagen that are not really made for AI projects. They're rather made for huge waterfall-like SAP projects, but not on, I want to build an AI that works and keep continuously improving it, but rather our company is still used and in some parts still is thinking in kind of waterfall projects, which kind of makes it very hard to implement these kind of projects. And of course, especially in Germany, but also in Europe general, data protection is a big thing. So we cannot just put a camera somewhere in our factory and then start recording pictures, videos or whatever. We always need to include the Workers' Council and data protection and make sure that everything's compliant to GDPR. So again, something that's, it makes a lot of sense, data protection, but in practice, sometimes it slows these kind of projects down. So a lot of problems. We used this to formulate some kind of vision you see here on the right-hand side. So until 2024, so actually this year, so good time for a snapshot, we wanted to build a scalable ICV ecosystem, and our key motivation as Volkswagen is to save money because car industry is very cost-oriented. So for us, the key lever is always improving our cost basis. So that's the target, and we define three key pillars how to implement this kind of scalable ecosystem. So we focus on the one hand on group-wide use cases that across all Volkswagen brands, so not only Volkswagen, but also Audi, Porsche, Seat, Skoda. 12 brands in our group, so a lot of use or a lot of factories and brands that can consume these kind of use cases that are scalable across locations. We wanted to work, on the other hand, on the democratization. So there are these big huge use cases you want and can scale, but on the other hand, there's a lot of local problems in your factories, since the factories tend to be different from each other, and they always have a lot of smaller local problems that they want to have solved. And in the end, it's too challenging to solve all these problems with a central approach. So you also need some kind of decentral approach to enable these factories to solve their own little computer vision use cases. And then IT foundations, and not only IT, but also processual foundations we built. So if you want to really have an ecosystem, this is not only implementing use cases, but also making sure that the processes around work and scale well. And I want to take you quickly through these three pillars and give you an insight on what's actually going on there. So we're starting with the IT infrastructure. Honestly, this is rather a marketing slide, a very high level on how these kind of computer vision platforms look like. We as Volkswagen decided to build our own because for these very special industrial use case focused like use cases, there was not really one platform that could solve everything. So you see here in the really heart of the platform was everything you need to build and operate AI. This is, of course, not really differentiating from everything else. Really differentiating us is rather the left-hand and the right-hand side. So we are connecting industrial cameras to our platform. Those are the ones that are approved by our factories, and they only want to use these kind of special industrial cameras because they're dust-proof, waterproof, and there's a lot of certifications these cameras need to go through. So that's a rather specific input layer here. And then, of course, the big challenge is to integrate this also into your production IT. So you need a trigger signal on when to take a photo. You need the meta information on what should actually be on the photo. And then somehow you need to write your information back to the whatever production IT system. This is quite a challenge because especially these PLCs, so PLCs are the little computers that steer single working stations within your factory. Those things are super reliable and super long-term living, so you come up with these things that are from the 80s sometimes, very good old Siemens computers, and you might expect that these things are quite difficult to handle with some kind of new AI technology. So there's a wide range of things you need to consider. So we implemented all of this ourselves. Most of it is cloud-based. We have a big partnership with AWS, and we are building together with AWS this kind of ecosystem to make these use cases work. What are the actual use cases? Probably more interesting to you. I brought the three things that we decided to implement initially. So out of these 100 plus that I showed you earlier, we collected the top use cases and chose these three as flagships to prove that industrial computer vision actually works, and then we can fulfill the requirements of our factories. I'll quickly guide you through. On the left-hand side, you see the label inspection, which we implemented in Porsche. You see here this little thing is called the type label. This is like the ID of the car. It needs to be in every car, and depending on which country and legislation you have, it needs to have different content. It needs to be turned around, it needs to be in different position. So there's a lot of individual legislations on where to put it and what to check on it. Of course, there's also Chinese type labels, and for a German worker who puts this label in, it's quite difficult to check the Chinese letters on if this is actually the correct label for the car that it's currently producing. So this is a perfect use case to demonstrate on what the potential of ICV is, because this is just too complex for a human to check, and a computer can do this quite not easily, but at least it can do it, and it can do it 24/7 without any errors. Then in the middle, you see the assembly check that we implemented in Wolfsburg, which is our headquarter of Volkswagen. You see the underbody of the car, and you might guess the underbody of a car has quite some complexity. There's a lot of different coverings and parts that need to be on the car, and it's very tailored to what kind of model you actually have, right? So a Golf can have dozens of these different underbodies. And again, the combinatory room is very large, so a human cannot simply look at the underbody of a car and say, okay, yeah, this is fine, continue. So once again here, complexity is very high, perfectly made for ICV. Adding to this, right, this is rather a simple object detection use case, so from the AI technology also solvable. And then the last one, a bit different in our press shops. We produce every 3 to 5 seconds. There's a new metal part coming out of the press shop, right? So something like a window or a door or something like that. So we really push the limits of the physical things. And sometimes every couple thousand parts, you see there can be cracks on the metal. And at the moment, there's a lot of humans at the end of the line, and they're visually checking if these parts are correct and there are no cracks in it. So you might think about it, if you do this for 8 hours, then that's quite a challenge to stay concentrated and to really find all these cracks that might come up every couple of thousand parts. So once again here, an ideal use case for computer vision. So these 3 things were the ones that we implemented, and I would like to give you a bit of insight on why this is actually quite complex. For us, the key goal is this number up here, so 99.6% is the overall end-to-end performance we need to achieve. This is the classical number that basically every IT system in our production needs to meet. Right? And if you want to make industrial computer vision really working and really integrated into our factories, you need to meet this figure, because otherwise you're just not fit enough for production. And even if you consider like we're building 100,000 cars every year, even these 0.4% end up to quite a number of cars. If you end up having this number of cars wrong, then this might end up with a bigger challenge. No, that's a very good question. It's not only the data science part, right? So this is what I wanted to show here. So the actual data science part is these 2 steps here, right? So you segmentate the label, crop it somehow, and then you read what's in it, and then you check if that's actually correct. This works extremely reliable. The key challenge for us is putting up everything else here. So actually taking the photos within the line on an extremely high reliability level. So cameras tend to break down, your trigger signal comes too late. All this ends up in you breaking this chain and not meeting this figure up here. And also a big challenge is this connectivity chain, right? So everything we did so far in the last centuries was always shop floor oriented. So we did every calculation we wanted to do within our factory, and actually bringing the data up to the cloud to actually operate it and run your AI model on it and get some kind of insights out of it is quite a challenge. And then, as I mentioned before, you also need to feed this back to the line, because if there's something not okay with your car and your AI finds out this is the wrong label, you actually need to take some action, right? So either you stop the line and then someone needs to come and check, or you write in some kind of backend system that this car needs to be double checked again. But again here, right? So if you have too many of these wrong, then there will be a lot of stops off the line. There will be a lot of cars brought to the rework area. So it's really no option for you to do some kind of guessing, but it really needs to be almost 100% reliable, but really from end to end, right? So your customer in the end doesn't care if it breaks down here, or if it breaks down here, or if it breaks down here. And even the latency requirements are quite challenging. So this whole round trip usually needs to take place within 10 seconds, sometimes even less. And so if there are any deviations on the connectivity chain, this already breaks your reliability figure. This is the classical IT SLAs we need to meet in our factories. So that's the platinum level, and everything that's really deeply connected into our factory process, this is usually the figure you have. Okay, so quite a challenging problem, but as I mentioned, the core AI part is not the core challenge, but it's really building something that's extremely reliable around this. How are we doing this? I mentioned earlier we're working very cloud-centric, so we try to move everything out of the factory because that's really hard to implement and also to operate. So we're moving to the cloud, and we played around a lot with finding good solutions on how we can make this extremely reliable. You see here we have a lot of different factories. Right? This is only indicative, right? But giving the idea. And in the end, you saw the use cases are very different from each plant to each plant, but also the IT systems you need to connect, the data you get is different. So you need some kind of abstraction layer to make sure that in the end, the operations you do with ICV are very standardized and similar. So our current approach is that every plant, every location has its own local cloud, so to say, where they do all the data processing, the preparation. And once you have a very standardized bundle of the picture with the meta information and the detailed information on what it needs to check, you send this package to our central cloud, and there's a big GPU engine running and sending this back within under 1 second of reaction time. And then whatever the outcome is, either the photo is okay, or the car on the photo is okay, or it's not okay, you feed this back to the line, and then either the line stops or the car goes somewhere to be checked again. So again here, cloud for us is quite a game changer. So making it scalable is very easy with cloud. That being said, I mentioned earlier, like this is not really the culture so far in our factory, so they are used to having full control over everything. So also convincing everyone that cloud is a good idea here is quite a challenge, and also includes some kind of cultural changes, not only technical innovations. Then one other thing I would like to point out, I mentioned the 99.6%. This also includes changes in your production process, right? So you might guess that from time to time these cars change that you produce, so you get a new generation of the Golf, or there's just a minor update, whatever, or some new kind of legal legislation. So in the example of the underbody, it can happen, or it does actually happen quite often, that these parts change, and you probably can guess it. For an AI, that's quite a major challenge, because actually you would then start collecting new photos, start labeling the photos, training new AI models and so on. And if that's not a car that's really numerous, then you need to wait quite some time until you have enough photos. So it's a big challenge for these kind of systems to stay up to date, and you actually cannot tell your customers all the time, okay, if something's changing, give me 3 months and I'll give you an updated version of your AI model. This just doesn't work. So what we are currently doing is to industrialize also synthetic data. The good thing is we always have 3D models of our cars. This is, of course, the key asset of our virtual engineering. And we take these kind of 3D data, the CAD data as we call it, and generate these kind of artificial photos. The good thing is we always know what's on the photo, so we don't need labeling for this kind of synthetic data because it already comes within the 3D model. And we can easily generate thousands, 10,000s of these photos right away with the 3D model. Even before the car has been produced once, so it really speeds up your learning curve a lot. We're still working on industrializing this. It works quite nicely once you make it work, and we're currently researching on how we can make this really scale across all kind of different use cases. Also with the labels that I showed you earlier, there's a lot of nice, interesting opportunities for using these kind of things. Of course, NVIDIA Omniverse is a very helpful tool here as well. And then the last pillar, the democratization, I wanted just to give you a quick insight on what it looks like. So our Volkswagen plant in Zwickau is one of our flagship factories here. They have a local team who focus on implementing these kind of use cases only for this kind of factory. And this turned out very nicely because they know their local situations, they know the local IT systems, they know the cameras the factory wants to use. So this gives you really a head start when you want to implement these kind of new ICV use cases. And I just brought 2 examples to show you. So a rather simple one, again, from the data science perspective, is the plug detection. So the humans need to put these kind of plugs into the holes here because the car body then goes into some kind of liquid, and then obviously if one of these plugs is missing, the liquid goes into the car body, and it's quite costly to get it clean again. So with a camera, we have a backup system now to check that all these kind of plugs are put in correctly. Again, here, imagine you're a human worker and you need to put in these plugs 8 hours a day, then it can happen, and it does happen, that you forget one, and it can be quite expensive if this happens and you haven't checked it. Another one, I put it in because it's some kind of, or not the typical computer vision technology. We use also in anomaly detections for some kind of use cases. You see here, there's sometimes workers forget their tools on the car body. Again here, this is right before the paint shop. So when the car gets in these kind of paint baths, And if you forget these kind of tools on the car, then there's a chemical reaction, and again, a lot of cost. So you really want to make sure that the car bodies that get into the paint shop are clean and there's no foreign objects on it. We tested the anomaly detection here, and it worked out quite nicely. Anomaly detection here is a bit different because you only feed in the OK photos, so how it should be, and then if there's a new picture coming in and the AI detects something that's deviating from the picture it has seen so far, it renders these kind of heat maps, which is quite a good technology for us, because we often have the problem that we don't have enough data on how the errors we want to detect actually look like. So these kind of anomaly algorithms are quite handy for us if we only have OK photos.
What if it's just a new level? Because that could also be an anomaly, right? Like imagine a new design opened up and I'm not seeing that.
Yeah, that was one of the outcomes. So these kind of algorithms are very sensitive towards any changes in the picture, right? So not only on the car body, but also if this changes here or the lighting changes, it's different if you take the photos in summer compared to winter, right? So again, coming back to the 99.6% reliability, this is an extremely tough job to meet. These kind of algorithms usually are good for backup systems that are not really 100% or that are not stopping the car every time that there's a detected error, but it's rather a supportive backup system. And then final slide, just to give you a quick outlook on, or a backward look as well. So I mentioned already, we started off a couple of years ago with some kind of typical storming phase. There were a lot of early POCs, as I mentioned already, that were individually organized with the IT or startups and so on. So a rather unstructured storming phase. Then for the last 3 years, we've been building this kind of strategic setup that I just showed you, and I'm quite happy that the picture I showed you earlier with our strategy hasn't changed throughout the 4 years, so that was quite a positive sign, I think. We built these initial use cases on top of a couple of other use cases as well. We built our own platform, and now we finally entered, and we are in the middle of the scaling phase now. So we're bringing this across all our factories. We implement a lot of different use cases. We were quite happy because we were also granted some kind of public research project, which gave us the chance to build some kind of consortium as well. So you see here, there's a couple of partners we work with. For example, Bright AI is a startup from Berlin that's focusing on anonymization of photos. Zeiss is leading in all kinds of 2 and 3D sensoric. So we're also researching now into making ICV also 3D focused and so on. So quite a great chance for us to make the scale. We're in the middle of it, so many use cases work right now in a lot of factories, and we're focusing now mostly on these kind of ML ops topics or general the operations topics to make sure we meet these 99.66 overall reliability. And that was our journey for Volkswagen. Any questions?
So how does that actually look like in reality? So let's say you're trying to create CAD versions of the underbody, the front cover of the engine bay. Then you have to generate multiples of those, right? So how do you control this process? How is it done, and how do you make sure that it doesn't break the model? Because if you go crazy, right, instant segmentation can flow over.
Yeah. Yeah, correct. It's very individual, right? So it's over. At the moment, I mentioned we're working on industrializing this. At the moment, it's really handcrafting everything. So you need on which combinations are there, how many photos is okay to generate, because it doesn't make sense to create 1 million photos. That doesn't help the model in the end. But it's a lot of handcrafting at the moment. We're still working on finding best practices that work for 80% of the use cases, but that's some way to go still. Yeah, there's a lot of challenges, and the tools tend to change depending on the problem. I mentioned earlier, like the lighting is a big challenge for us. So taking photos in summer is different from the photos you take then in operations in the winter. We use different drift technologies, for example, to find out if there are things deviating. We also implemented a 24/7 support because our factories are running 24/7, so we also need at night some people who are there, and we're currently finding out ways that people in the night shift are looking at photos and checking if the confidences are going low and so on. So there's a lot of different technical and organizational processes that we're checking. At the moment, it's still very early phase, so it's not really scaling in a sense that it's cheap. That's hopefully then the next step once we make it work.
Volkswagen vehicles are very famous for quality, so quality is already good. So what kind of improvement do you expect? So is it technology to replace current quality control, extend, or introduce the new ones?
Yeah, it's a bit a mix of everything. So at the moment, in every car factory, there's a lot of visual checks still. So a lot of people are there not only doing visual checks, but also like while they mount something, they also do some visual checks, right? So this is things we want to get out of the production process because it speeds up the process. Also, we have the vision that, of course, we want to automate processes further and further, and at some point you will not have enough people to react or to find out if there are quality problems in the line. So in the end, you need this kind of technology in a fully automated process as well to make sure that the car that goes out at the end of the factory is the actual car you want to build. And there's also some quality assurances. We also have the situation that we get parts from our suppliers and they tend to be wrong or they have the wrong labels. So we also need to check these kind of things. So there's a lot of potential for the technology. But in the end, yeah, most of it is working towards maximum quality.
So does it mean that people will lose jobs by introducing technology? Sorry, but actually you didn't answer my question.
Yeah. We want to reduce workforce there, yes, full stop. But we're not there yet because usually, as I mentioned, at the moment, these visual checks are usually just a fraction of seconds of what people are doing, right? So you need to do a lot of these kind of use cases until you have the first person you can put somewhere else in the process. So I would say for the next 3 to 5 years, this won't be the key lever to reduce your workforce, but in probably 5 to 10 years, it will be. Yeah, again, the labeling is very depending on every use case, obviously. Sometimes you really need the engineering experts from your production to label it because it's super hard to identify, is this actually a crack or is it not? Because sometimes the cracks are really, really small, and if I look at the photo, I won't ever recognize the crack. Sometimes it's rather simple, like these kind of underbody checks, right? So it's big parts. This is rather easy to label. In those cases, we usually use some external service providers. We write a labeling guide, put it over, send them, I don't know, 10,000 of these photos, and then they give them back to us labeled. One last question, maybe in the back.
Thank you. I assume that you're using like traditional computer vision, pre-LLM neural networks, like the specialized one, OCRs and clustering. What do you think are the possibilities for using multimodal networks and being able to actually capture digital information and then ask questions to that information for your use cases?
At the moment, we haven't focused on that because our current focus is really on making it super reliable. I personally haven't thought a lot about LLMs yet because we're still focusing on making this work.